I'm going to go through some useful results from vector calculus as they apply to electromagnetism. We're going to start by considering the gradient of 1 over r. Now, excuse me, we defined, remember that we're thinking about 2 points because we're generally considering a field at a point r1 due to some kind of source at a point r2. So we're going to think about the vector r21, which we're defining as r1 minus r2, and that is the vector which goes from r2 to r1. If we draw a little origin here, put r2 over here and r1 up here, so those of course are the two vectors. And we see that in order to go from r2 to r1 we have to come, let me just change the colour here, we have to come back down here, that's minus r2, and we have to go back up here, that's plus r1, and so the final vector result is r21 here, which is r1 minus r2. Now, the point is, when we take the gradient of this, we have to be a little bit careful. So let's start by writing down the magnitude. So r21, which is the magnitude of r21, the vector, is going to be the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, and that's all under the square root sign. Notice, of course, that as you would expect, it doesn't matter which way round the 1 and the 2 are, because this is a magnitude, this is a distance. So let's think now about the x component of the gradient with respect to r1 of 1 over r21. So I'm going to put square brackets with a little x at the bottom to indicate that we're taking the x component. And that, of course, is just d by dx1 of 1 over r12, which is, if we're going to write this out fully, is d by dx1 of x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared, all to the factor of minus a half. So let's do the differentiation. And when we do that, then the first thing we get is minus a half. Oops, that's a little bit messy. Minus a half, that's the that's from the square root, the 1 over the square root, the power on the bracket, multiplied by d by dx1 of x1 minus x2 squared, multiplied by, I'm going to put square brackets around this, x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. This is now to the minus 3 over 2, because when we differentiate we subtract 1 off the power. And that, of course, is equal to minus a half multiplied by 2 x1 minus x2, that's the differential of the bracket, multiplied by 1, that's dx1 by dx1, multiplied by 1 over r21 cubed, which is just minus x1 minus x2 over r21 cubed. We could do the other components, but it would be identical. And so what we can conclude is that the gradient with respect to r1 of 1 over r21 is given by minus r21, the vector, over r21 cubed. Of course, you could write this as minus r21 hat over r21 squared. You can also note that it's equal to r12 over r12 cubed, because r12 is just minus r21. I've changed the order of the numbers on the denominator there, r12 cubed, just to be clear. Of course, it's the same number. And it's very easy to show that the gradient with respect to r2 of 1 over r21 is just r21 divided by r21 cubed. And so you see that they have opposite signs, but the same direction and the same magnitude. And that makes sense, because if you think about differentiating, so let's say that this is the vector r21, this is R2 and this is R1. We're differentiating a magnitude, so of course it doesn't actually matter where we put them in space, and so differentiating with respect to R2, let's say if R2 moves inwards, that will be equivalent to R1 moving outwards, and so of course they have to have an opposite sign. It's really important to notice this kind of trick, and particularly in electromagnetism, to spot the fact that you've got a vector divided by its cube. We will frequently use that to simplify things. I'm now just going to make a couple of notes on the differential identities. And so the differential identities I'm going to consider are the following. So first of all, we've noted that the curl of the grad of any scalar function is always equal to 0. And we've also noted that the divergence of the curl of a vector function is always equal to 0. We can, of course, do the maths, and you can see that they are identically 0, but the other question we might want to ask is, intuitively, why is this happening? So let's first of all think about the way that we write a curl. So we have curl of f, and this is going to be I, that's the unit vector in the x direction, of df z by dy minus dfy by dz plus j multiplying dfx by dz minus dfz by dx plus k times dfy by dx minus dfx by dy. And you can loosely characterize the curl of f as relating to how much it swirls, how much of a rotational motion there is in f. So now if we think about f as being equal to grad v, then that tells us that fx is dv by dx, fy is dv by dy, and fz is dv by dz, of course. And mathematically, if we now look at one of these terms, let's look at this x term here, then we see that when we take the divergence of the curl of v, so if we're considering now, sorry, the curl of the gradient of v, I misspoke, I beg your pardon. When we take that curl, we're taking the curl of this little f that I've written just up here, and so the first term is going to be dfz by dy minus dfy by dz, and fz is just dv by dz, fy is dv by dy, and so these two terms are going to both be identical. So what we'll see is that we've got I times d2v by dy dx. No, that shouldn't be dy dx, that should be dy dz. Minus d2v by dz dy, etc. And unless you are dealing with a very peculiar situation, we can switch the order of the differentials and we will of course get 0. Intuitively we might say that the curl is looking at how much of a swirl there is, and of course a gradient isn't going to swirl, it's not going to go around a point because it is necessarily going downhill. So you could argue that that's the intuitive understanding of why that's always equal to 0. Similarly, when we think about the divergence, if we just write out simply the divergence of the curl of f, which is equal to 0, well actually let's not jump the gun. Let's we have dfz by dx dy minus dfy by dx dz plus dfx by dy dz minus dfz by dy dx plus dfy by dz dx minus dfx by dz dy. And we'll see that this first term 1 cancels with this fourth term here, so those are the z by xy's. This second term, the dfy by dxz, cancels with this second term here, and this third term here cancels with this term over here. So that's why then it's equal to 0 mathematically. Now let's think about what divergence and curl mean. So again, curl is roughly speaking a swirl and a general tendency for something to go around, whereas a divergence is the tendency for something to spread out. And so if a vector is forming loops, then it's not spreading out at all. It's not expanding or contracting. And that, roughly speaking, is an intuitive picture of why that's happening. If you wanted to, you could just assume that you have a field which is only along z, and if it's only along z, then the non-zero components of the curl are in x and y. So in fact, let's just write this one out. If we say that f is equal to fz in the k direction only, then the curl of f, if we just come back up here, the curl of f is dfz by dy in the I direction minus dfz by dx in the j direction. And that starts to look very much like circular motion in the xy plane. That's completely confined to the xy plane, and when we take the divergence, that is going to go to 0. So those are some simple results on vector calculus. I hope they're useful. It's very important that you learn how to use vector calculus and become very familiar and happy with the way that these things work for electromagnetic theory.